All right, AVID focused note taking. We are on Chapter 3, Lesson 3, Moving Plates. Okay, first thing's the same. Write your name. AVID 6 for the class or period. Monday's date is November 2nd, 2020. Science, FNT, Phase 3, Connect. Remember, Phase 1 is taking notes. Phase 2 is processing by highlighting and annotating the key details that support the main idea. Chapter 3, Lesson 3, just like the format on the AVID Cornell Notes page. Okay, Moving Plates in blue is our title for this lesson. Main idea, essential question. And then have your pencil, and here we go. Heat from Earth's interior drives convection currents in the mantle. So Earth's interior is the inside. Convection currents, we're going to learn what those are. And the mantle, remember, that is the big thick layer underneath the crust. Heat, capital H-E-A-T, from F-R-O-M, Earth's, capital E-A-R-T-H, apostrophe S, interior, I-N-T-E-R-I-O-R, drives, D-R-I-V-E-S. And when they say drives, they don't mean like driving a car. They mean that the heat is forcing these things to happen. Convection, C-O-N-V-E-C-T-I-O-N. Currents, C-U-R-R-E-N-T-S. N-I-N. Mantle, M-A-N-T-L-E. Period. These currents move tectonic plates at rates of centimeters per year. Move, M-O-V-E. Plates, P-L-A-T-E-S. Arrow, C-M for centimeters. A slash for a divided or per. Year, Y-R. Centimeters per year. That slash is the same thing as a divided by or a fraction. Centimeters per year. Okay, vocabulary words. Convection, skip a line, C-O-N-V-E-C-T-I-O-N. Page 110, turn one page. Convection is the transfer of thermal energy by the mass movement in a fluid such as air, water, or molten rock. Okay? Transfer of thermal energy. That means that heat is moving. Mass movement, what they mean is the actual physical stuff is moving. The fluid is swirling, or the air is blowing, or the water is swirling, or the molten rock is swirling. Here's a picture on page 110 that shows convection currents. If you have heat underneath, it's pushing up, and then as the magma heats up, it swirls, and when it gets higher and higher, it starts to cool down, and then it will fall. But it gets close to the hot stuff again, it warms up, it rises, it cools down, it starts to fall again. And that's a convection current in the mantle under the earth. Okay? Transfer, T-R-A-N-S-F-E-R. Thermal, T-H-E-R-M-A-L. Energy, E-N-E-R-G-Y. By, we're going to make a little space to indent, B-Y. Mass, M-A-S-S. Movement, M-O-V-E-M-E-N-T. So we know that transfer is to like take something from one place to another. So transfer is going to be movement. And they said movement by mass movement. Thermal energy, that's heat. Mass movement for the mantle and for the earth, that's going to basically be a swirl. S-W-I-R-L. And we'll put that in quotes. It's like a swirl. It's like something moving in a constant circle. Okay, next one, convection current. Skip a line because we have that word there in the way. C-O-N-V-E-C-T-I-O-N. T-I-O-N, current, C-U-R-R-E-N-T. In a convection current, convection drives the fluid through a circular path. Okay. Drives, D-R-I-V-E-S, circular, C-I-R-C-U-L-A-R, path, P-A-T-H. And the easiest thing to do is let's just draw a circle. Okay, we're going to do it similar to what they have right over here. So we're going to start with an arrow pointing to the left and down, arrow pointing down. Now it swirls back around this way, swirls up over that way, swirls up over that way. So now we have our circle, our circular path. Over here, we're going to draw a double arrow line and put heat, H-E-A-T, because when something is hot underneath, it pushes up or drives that circular path. And then over here, we're going to put cool, C-O-O-L, and two little down arrows. So as the heat source, the magma, M-A-G-M-A, heats things up, it pushes up and starts this swirling motion. Once it gets over here and cools down, it's going to fall because it's more dense, and it starts that circular path. That's a convection current. All right, oceans and continents. Find where your magma is and skip a line. Capital O-C-E-A-N-S. And down 3 down. Continents, capital C-O-N-T-I-N-E-N-T-S. Switch back to our pencil. When scientists began studying the ocean floor, they expected it to be much like the land they had left behind. Instead, they discovered some important differences. Okay, so scientists started studying the ocean floor and they realized things are different, like we learned in last lesson. Continental crust is composed of granitic rocks. That means granite. So like when you hear people talk about a granite countertop, that's what they're making their countertops out of, this granitic rock. Granitic rocks are made of lightweight minerals, such as quartz and feldspar. Okay, that's important. So, crust, C-R-U-S-T, but it's not just crust, it's continental crust, C-O-N-T-I-N-E-N-T-A-L. So, not the crust in the oceans, only the crust at the continents. Continental crust equals granitic, G-R-A-N-I-T-I-C, and that equals less, L-E-S-S, dense, D-E-N-S-E. And let's draw a little arrow up so that we know that kind of makes it float, F-L-O-A-T, in quotes. Right, so when something is less dense, it tends to float on top. When something is more dense, it tends to sink to the bottom. The granitic rock is less dense than this basalt ocean crust, so it tends to float on top. All right, let's see here. Where are we? Oceanic crust is composed of basaltic rocks, such as basalt and gabbro. These are igneous rocks, meaning they formed from hot, molten rocks as they cooled. Okay, oceanic crust. O-C-E-A-N-I-C, oceanic crust, C-R-U-S-T, equals basaltic, B-A-S-A-L-T-I-C, equals more, M-O-R-E, dense, D-E-N-S-E. Arrow down, quote, sink, S-I-N-K. Okay, and then what else did they say? They said igneous, formed from hot molten rocks as they cooled. So we're going to skip a line for the sink. Igneous, I-G-N-E-O-U-S, equals magma, M-A-G-M-A, arrow, above that, cooled, C-O-O-L-E-D, and they said it cooled into these granitic rocks. So, rock, R-O-C-K. So igneous means that magma cooled into solid rock. Basaltic rocks are denser than granitic rocks. Okay, we have that here. Basaltic rocks are more dense than granitic rocks, which are less dense. Okay, the illustration on the next page shows how scientists understand Earth's crust today. That's this picture. So, the asthenosphere is this dark orange part. All of that is the mantle. This part up here is the crust. The crust and the upper layer of the mantle together are the lithosphere. So the gray part and the tan part are the lithosphere together. The continental crust is this less dense granitic rock. The oceanic crust is the more dense basaltic rock. You notice they're two different colors, two different compositions. Note that continental crust is much thicker than oceanic crust. Ah, okay, let's put that somewhere. Not only is the continental crust less dense, it's also thicker. T-H-I-C-K-E-R. And over here in basaltic, let's put thinner. T-H-I-N-N-E-R. On average, continental crust is about 40 kilometers thick. Under oceans, the crust typically is about 7 kilometers thick. Okay, we don't need those specific numbers, we just need to know that one is thicker than the other. Earth's vast oceans cover a rocky floor. These rocks are denser than those that make up the continents. The photograph shows the coast of California and the Pacific Ocean. Okay, we have all that information in our notes already. Here is a cross-section of Earth's crust. We already talked about this picture. Let's move on to floating plates. Red pen, red pencil, red crayon, skip a line, capital F, L, O, A, T, I, N, G, floating, plates, capital P, L, A, T, E, S. Switch back to your pencil. Earth's crust and the rigid upper part of the mantle together form the lithosphere. Okay, we already know that. We already know that the crust, this gray part for the continental, or this dark part for the basaltic, plus this little tan part, that's the upper mantle. From there all the way out is the lithosphere. And that's how you can see that little bracket right there lines up at the top. That little bracket lines up at the bottom of the tan part. So those two layers together are the lithosphere. The lithosphere is broken into sections called tectonic plates. Underneath, the mantle is hot and plastic-like. This part of the mantle is called the asthenosphere. Okay, so let's see. Floating plates, lithosphere, L-I-T-H-O-S-P-H-E-R-E, arrow, plates, P-L-A-T-E-S. So now we know that the tectonic plates are broken up on the lithosphere. It's going to be the crust and the upper mantle. Why doesn't the lithosphere sink into the hot layer below it? The reason is that the rocks in the asthenosphere, remember that's this hot part down here, are denser than the rocks above them. Both the granitic rocks on land, that's this gray part, and the basaltic rocks of the ocean, that's this part. So even though these are cool and hard, they are still less dense than all the stuff down here. So all the stuff down here still stays sunk at the bottom. Okay, where were we? You can think of Earth's tectonic plates as giant slabs of continents and ocean, all afloat on a sea of soft rock. Interesting. Okay, so the lithosphere is broken up into the plates, and it is less dense than the asthenosphere. A-S-T-H-E-N-O-S-P-H-E-R-E. So it tends to float. F-L-O-A-T. Alright, so the crust. Either the continental crust, which is granitic, or the oceanic crust, which is basaltic, is solid and hard rock. Both of those combined with this upper part of the mantle are the lithosphere. All that lithosphere is what's broken up into the tectonic plates, and all that stuff is less dense than the asthenosphere. down here it's very hot and kind of soft plasticky fluid. I would say almost like a really thick honey, or kind of almost like a Play-Doh consistency, and it's so hot that it causes that swirling motion. Density also explains why continental crust is much thicker than ocean crust. Granitic rocks are less dense than basaltic rocks, so continental crust can grow thicker than ocean crust and still float on the asthenosphere beneath. Ah, okay. So this is more dense than the granitic rock. If it gets too thick, it would just sink into the asthenosphere. The granitic rock is less dense, so it can grow thicker before it gets too heavy to fall in. Okay, that kind of makes sense. So let's find out, let's say something about that. The thicker and the thinner is tied to it being less dense and more dense, right? Granitic rock is thicker, partly because it's less dense than basaltic rock, which is thinner because it's more dense. Let's see, where are we? We read all of that. We read all of that. Much like other things that float, Earth's tectonic plates are in constant motion. They slam into one another, slide over or under each other, and grow larger or smaller. Yet the total size of the planet is not changing. This means that if one plate is enlarging, another must be shrinking. You will learn more about these motions as you read on. Okay, so under floating plates, we learned that the lithosphere is broken up into the tectonic, T-E-C, T-O-N-I-C, plates. All of the lithosphere is less dense than the asthenosphere, so it kind of floats on top. For lithosphere, let's put crust, C-R-U-S-T, plus upper, U-P-P-R-E, mantle, M-A-N-T-L-E. If we need to know what that looks like, we can always come back to the book, or we can go all the way back to Chapter 1, Lesson 2, Earth's Structure. That was the second set of notes we ever took. And if it's Earth's structure, then we talked about Earth's layers. And here is our drawing of the layers. There's the lithosphere. There's the crust where all life exists. It's thin and rocky. And then here's the mantle. And you can see from the little bracket we drew that the crust and the upper mantle make the lithosphere. So everything we learned in this chapter, all the way back then at the very beginning of school, 2 months ago, is now important again. And that's why it's so important to take notes every chapter and learn every chapter. All right, the last thing to look at is our draw conclusions. Why don't continents sink into the mantle? Okay, remember continents do not sink into the mantle because the granitic rock is thicker than the ocean crust, allowing it to be less dense. Actually, let's say that the other way around. The granitic rock is less dense, allowing it to be thicker. The basaltic rock is more dense, allowing it to be thinner, right? They do not go into the upper mantle because both are less dense than the asthenosphere. So, why don't continents sink into the mantle? Continents float on the mantle because everything in the lithosphere, the crust in the upper mantle, is less dense than the asthenosphere. Okay, so we have all the information we need right here in floating plates and in oceans and continents to answer that question. Since we have all the information we need, then that means we're done. Okay, we did all the pictures, we did everything else. Good job persevering with the growth mindset, and roar Wildcats!